Hello everyone and welcome to another Advanced Maths differentiation video lesson. What we're going to do in this lesson is take a little look at knowing when and how to use logarithmic differentiation. So, criteria for the lesson: I want you to know when to use logarithmic differentiation, so I want you to be aware of the types of functions that it's particularly useful for as a technique, and then I want you to know the process. So the process involves taking the logs of both sides and then from that obtaining and simplifying the derivative using implicit differentiation. So what you were learning about in the last lesson applies here. So let's take a little look at what types of functions we would use this technique for. Well, if you have a little look, the first bullet point there is we would consider this technique for functions where the power itself is a function of x. So any sort of exponential function where the variable is the power, so 5 to the power of x or x to the power of x is the sort of thing we're looking at there. It's also very useful for functions that involve lots of brackets. This here, you could, in theory, use the quotient rule to differentiate it, but then if you get further down into that, then the numerator needs differentiated using the product rule, and each of the brackets needs differentiated using the chain rule. So there's really, that's just too complicated a way around. It would work, but it would be quite a task. So we use logarithmic differentiation for things like that. So let's take a look at the process. So here's the first one you saw there, which was 5 to the power of x. Let's take a look at its derivative. Now, the first thing to do is to take the logs of both sides. Okay, so take, gee whiz, what's going on with that? Pen tool. There we are. So take logs of both sides. So log y equals log 5 to the power of x. And the reason that's beneficial is because we can use the log rules to get the variable off the power. Yeah. So using the rule from higher maths, log y becomes or log y now equals x log 5. Okay, so now we're ready to differentiate. If we look at the terms, log y is easy enough to differentiate. If you think about log x, its derivative is 1 over x, so the derivative of log y will be 1 over y dy by dx. Okay, that is equal to the derivative of x log 5. Now, you might be fooled into thinking that you need the product rule to differentiate a term like that, but you don't, because log 5 is just a number. So you would just differentiate it as if that was saying 2x instead of x log 5. And now, of course, the derivative of 2x is just the number 2, because the derivative of x is 1. So the derivative of x log 5 is just log 5. Now, to tidy this up, we want dy by dx on its own. So this is going to be y log 5. But it's not really any use to me written like that. Ideally what I want is the derivative in terms of x. So we need a substitution for y. Well, hang on. It tells me up here y is equal to 5 to the power of x. So my derivative now looks like this. 5 to the power of x log 5. Okay. So not that tricky when you get down to it, but you know, the process itself, take logs of both sides and then tidy up your derivative. Remember, when you're doing this, to use implicit differentiation. Let's have a little look at another one. So let's take a look at x to the power of x. Start with the same first step. Log y equals log x to the power of x. X comes off the power. Log y equals x log x. Oops. Right. Now, whereas in the last one we had x log 5, so we didn't have to use the product rule, but for this one we will have to use the product rule because log of x is not a number. It represents a number, but it's got the variable x in it, so it has to be differentiated with respect to x. So this has to be differentiated using a product rule. So let's do the prep work. X log x, u equals x, u dashed equals 1, v equals log x, v dashed equals 1 over x. Right? So our derivative, 1 over y, dy by dx, equal to uv dashed, so x times 1 over x is 1, equal, plus vu dashed, so plus log x. Multiply up by y, and dy by dx is y times 1 add log x. Okay, make our substitution back for y. Y is equal to x to the power of x, so dy by dx is equal to x to the power of x 1 plus log of x. Okay, job done. Now, this next one we need to be a bit more careful with. Same first step, right? So we'll rattle through the first couple of lines quite quickly. Let's start with log y equal to log of sine x to the power of x. Get x off the top and we'll get log y equal to x log of sine x. Now, log y we can differentiate, that's no problem, but that is differentiated using a product rule. So x log of sine x. Now the thing about this, you have to be very careful and take your time when you are differentiating something like this, because the product rule itself is quite straightforward. U is x, u dashed is 1, v is log of sine x. Actually taking time to prepare like this is really going to benefit you because you can get quite a simple derivative from this. Now, quick recap of differentiating logs. Remember that log of f of x, the derivative of log of f of x is f dashed of x over f of x. So if we apply that here, f of x is sine x, its derivative is cos x, so this is cos x over sine x. Now, cos over sine is 1 over tan, so we're using our new trig identities we learnt about a few lessons ago, and 1 over tan is equal to cot x. So actually, taking the time to prep all of this instead of doing it in your lines of working over on the left hand side here can really help you, because now I'm just going to put x cot x in for uv dashed rather than x cos x over sine x and have to tidy that up. So take the time to prepare these things, because when you do, you might well find that you can do a lot of your simplification in your little side bits of working rather than in your main body of working. So let's march on. 1 over y dy by dx equal to uv dashed, so x cot x plus vu dashed, so plus log of sine x. Okay, now we need to multiply up by y, so dy by dx equals y times, we need to put all of this in a bracket now, x cot x plus log of sine x. Okay, make our substitution for y. Well, y is sine x to the power of x, so dy by dx, let's finish it off, dy by dx equals sine x power of x times x cot x plus log of sine x. Okay, and that's it. That's all there is to it. Right, let's look at another one. This time it's differentiate y equals 2 to the power of sine x. Right, so let's get these first couple of lines done nice and quickly because they're pretty box stands for most of these. Log y equals log 2 to the power of sine x. Sine x comes off the top and we get log y equals sine x log 2. Right. This does not need a product rule because log 2 is just a number. So let's just get our derivative, 1 over y dy by dx equal to sine x becomes cos x, and log 2, if you think about it, if that was just 2 sine x, its derivative would be 2 cos x. So its derivative is cos x log 2. Right? Or you could write it as log 2 cos x. Doesn't really matter. I probably will just do that in the next line of working though. Multiply up by y, dy by dx becomes y times, and I'm just going to write log 2 cos x. Alright. Y is 2 to the power sine x though. So dy by dx equals 2 to the power of sine x, and then log 2 cos x. Okay. So, as a straightforward, it is a fairly straightforward process, a lot of these. As long as you remember to take logs of both sides at the start, bring your variable down off the power, and apply any other techniques you might need to use differentiation wise. So product rule almost certainly, you never know, you might need the chain rule in there as well, but you get the idea. The last example, right, I've decided I'm not going to do this last example within this video because I would imagine that by the time you've got to the point where you're watching this video, you will have casted your eye over the notes file, and the notes file that I've posted with this video takes a full typed A4 sheet to run through all the simplifications for this. So what I want you to do is look at this, look through this example, right? Look through it, and if there's, it should be fairly self-explanatory, the way I've put it down in the notes and things like that, and I've taken great care to put a lot of lines of working into it. As I've said before in other videos, some of you guys might be better, or not better, but you might find it a bit easier to put more or to skip lines of working out more accurately. So I'm going to leave that one up to you. So I'm not going to do this example as a video unless there is quite a bit of demand for it. So if the notes really doesn't make any sense to you, please email me and say so. And if enough of you do that, then I'll stick it down in a video. But you know, I'm already at sort of 14 minutes coming up on, and it would probably take me easily another 10 to go through this. And as I say, there's just loads and loads of algebra involved. So make sure you do watch the video. Not watch the video. Make sure you do. Well, I watch the video, but make sure you read the notes. Right, read the notes that I've posted to go with this, so that you can look through a solution to this example. Okay, folks. So well done so far, and I'll see you on the next video. Listen, guys. Thanks very much.